I remember. Okay, we are solving one system of the linear equation in 3 dimensions, no? That one. Entonces, I want to, explain quickly because I explained something. And also, I want to take advantage to solving using the algebra. Okay. Okay. This is the system. Totally determined because 3 equation 3 unknown. That one. Okay. Entonces, I need to solve it. Guy, in the test, one question using Kramer rule. So you solving by echelon, no credit. So it's Kramer rule, Kramer rule. Now, I determine D with the determinant of the matrix formed by the coefficients in front of the variable. So now we compute by hand the value of this determinant using the cofactor formula, no? So normally, si there are no any problem, I prefer doing using the row one. So you expand the row one to say is, let me show you, let me make it zoom. Look, this one is this one. And when you delete this row and this column, stay this determinant. It's exactly I copy here. You see? Y this determinant is pretty easy because it's negative 2 times negative 2 is positive 4. And 3 times 1 is 3, but when you multiply in that direction, you include one extra negative 1. You remember very well this, right? Not necessarily explain again this, no? Okay. So you separate the problem in 2 by 2 determinant. It's super easy, right hand, and the answer is negative 3. So I reserve this answer for the future. Now you compute dx. Dx is easy. It's the same thing, except you taking the right-hand side number and you replace the column of the x. That is the reason que es dx. And we are doing exactly the same. dy, you replace the column y and the original d by the right-hand side number, that is 6, negative 5, or 14. And like what happened in this column. After we compute everything, okay, I have in my hand 4 values. You apply the famous formula of the Kramer rule. So the x value is the division dx divided by d. In this case, there's the same value. This reason gets positive 1. Y is equal negative 9 over minus 3 is positive 3. And c is dz is 6 positive. And d is negative 3 always, entonces es negative. And the solution is the point 1, 3, negative. Everyone understand very well this or no? Okay, question, come on. Or opinion. No necessary questions. You understand very well, no question. Super clear? Say something, guys. Say something. Clear, okay. Jonathan says it's clear. Shane is clear. Everything okay? Alison, Rebecca, Jose, Ardila, Leila, David, Sebastian, Janice, Daniel, Sidney, Michael, and Jonathan. Okay. Entonces I want to illustrate you, why not, how we solving this system in GeoGebra. Okay, you let me know if you see my GeoGebra get open already. Switching to GeoGebra. GeoGebra Classic. Do you see that?
Yes.
Uh-huh. When you open this the first time, you see similar to this. And you set out the window properly to work it with the matrix. So it's basically select view. No graphic anymore because I don't want graph. I want computer assistant software and a spreadsheet. Okay, a spreadsheet is my matrix editor. I put the width of the window in the way you consider better for you. Okay, let me manipulate. So D is the matrix. Let me start here in this cell. I have in this moment my keyboard, or you can use in this keyboard. It's available. Either way. But either way, let's do it this. Why not? One. I press in my keyboard manually tab. One. Tab. Negative one. Present. I press 3. Negative 2. Hey, noise. And wait, who make the noise? Who make the noise? Gustavo, no? Okay. Putting off the microphone. Okay, now we continue. Last row, A1. And negative 2. Okay, no noise, please. Okay, unbelievable. Okay, so now I take advantage. Why not? I want to create the matrix. You select the numbers, the array of number, create a matrix, and rename, of course. Because I want to put a capital U, capital A. I don't detect who is making mistake. I see any microphone off. Only my microphone is on. Okay. Okay, so the name, the new name, rename, and you compute the terminal. I don't finish to typing, however, you see the command, the function determinant matrix of the capital. The answer is negative. Cool. Okay, now in this moment, why not I type in here the right hand side number, okay, 6, no? Positive 6, negative 5, yeah, and 14. Okay, so I replace this in the corresponding column. So for doing that, we can do it in that way. You copy this, paste 3 times, one time for X, one time for Y, one time for 6, and you replace the corresponding. Suppose this, I copy and paste here. Cool. Paste here. and paste and compute dx, dy, dc. Just doing quickly because it's easy. Create matrix. This is the matrix, is the name of this is dx. And compute the determinant also of the matrix dx is -3 again. Si es -3, the reason is because x is 1. Remember to find x, you divide this divided by this. So basically the formula for the grammar say x is equal, you divide, let me see if I can copy this. No, in case speaking. Well, okay. No, you type it. Well, this is obvious. -3 divided by -3 is 1. Let's do in the complicated part. The complicated part is this. Select this is dy. Create the matrix. This is dx. Rename. dy. Sorry. Continue dy. Okay. Now the determinant dy is dy is center and -9. So therefore y is the -9 divided by -3 is positive 3. Now finally dc. Select, create the matrix. Okay, this is dz, rename, dc name. Okay, and determinant of dc is dc is 6. The c is 6 divided by -3 is d. The answer is negative, and that's it. So the complicated part, the division, this arithmetic, we can do if you want here, but no. All right, let me see if possible. Oh no. Yeah, that's possible. You put equal sign. No. You put equal sign. You put determinant d, determinant dx, for example. Let's do at least one. Determinant d dx, sorry. So the parenthesis actually is closed. Division is here. Where is division? Division is here. Divided by determinant d. Okay, of d. Equal enter. And what? Any question, guys? Super clear? Super clear. Of course, you have to practice, and you solve the majority of the problem in the test using your except some question gets mandatory to do it by hand. But this is basically it's similar to the review. When you see the review, you understand what part is by hand and what part is not by hand. It's just using the solve. Cool. Let's move on to the next topic. The next topic today is, let me come back again to whiteboard. Okay, switching to whiteboard. Okay, whiteboard. Okay, so now, next topic. Do you see my whiteboard or not yet? It's complicated. Do you see or not?
Yes, we did.
Okay, cool.
Yes.
Okay. Let me try to find I send attachment with the video, with the email. Okay, I send the link of this lecture. I send one PowerPoint about this lecture. No, this is the title of the lecture is Operation on Matrix. We're doing Operation on Matrix. What operation? Well, the arithmetic operation, addition, subtraction, multiplication. After you see the application, we ending when you see application of the operation of the matrix and what part you utilize. That one. Okay. Suppose one elementary example. Suppose you have two matrices, A and B. By the way, both are the same dimension, 2 by 3, because I can see, okay, we have two rows and three columns. And B is exactly the same, different number inside, of course. But so now, when you adding or subtracting, it's super easy, it's elementary. You adding by subtracting in the corresponding position of any entry. You adding 3 plus 5 is 8. And so on. Minus 7, minus 2, negative 9. 0 plus 8, positive. And so on. A subtraction is similar. Subtraction is, well, as we are doing in subtraction, okay, you, for example, the first entry is 3 minus 5, no? That is 3. But I change the sign of this 5 because of subtraction B, no? Minus. Entonces negative 2. Okay, this is negative 2. And negative 7, suppose negative 7, copy, negative 7, minus 2 que es plus 2. Es negative 5. Super clear? Important. To add or subtracting to matrix, the matrix must have the same dimension. So it's impossible to suppose the matrix A, que es 2 by 3, adding with the matrix B, que es 2 by 5. Illegal operation. And si es the same dimension, yes. So 2 by 3, 2 by 3, or 2 by 5, 2 by 5 both. Okay? This is the first operation we will do, addition and subtraction. Okay, now let's move into the operation property. Okay, and the addition subtraction property, oh, it's easy, very easy, similar to the basic algebra of the number. Normally, the matrix is the object, the algebraic object, multi-dimension. So si es 3 by 3, you have 3 dimensions. So now you have a scalar. Scalar is just a number, 5, 10. It's no. So before study matrix, you manipulate the algebra using a scalar. Bueno, in trigonometry we study vectors, que es one particular case of the matrix. But in this case, we are talking about matrix. O sea, A plus B is the famous commutative property que everyone apply. A plus B is equal to B plus A. So it doesn't matter the order to adding or subtracting. It doesn't matter. The order is not important. And addition. The subtraction, of course, yes. Associative property, when you have 3 elements, ABC, you adding in the order that you prefer. You put a parenthesis here to indicate you adding A plus B first. And then finally, the answer A plus B, you adding with the C. And see, you are doing in different order, the answer doesn't change. So you subtract the two matrices, A minus A. A actually is not 0, it's null matrix, que ese matrix forma, suppose que the original matrix A is 3 by 3, remember, 3 by 3, entonces now is 3 by 3, like that. Actually, this 0 null matrix contain 9, 0, no? Pero no es a square. Suppose another matrix is 0, 2, 3 is 2 row and 3 column, no? It's another null matrix in other dimensions. So the difference between matrix is an object that contains higher dimension. Okay? And the beauty is, the thing you want to see when I finish this chapter, this topic, is that you can manipulate, for example, 160 que contain 3 equations. You manipulate like one object. Okay, of course, this new object is a matrix, is 3-dimensional. So the algebra, you are doing no equation by equation separately. No. This is another chapter. No. Now you manipulate like a one package. Okay, 3-dimensional, 4-dimensional, 5-dimensional, and so on. And the last property is trivial. Any matrix plus the null matrix is equal to the original matrix. No? And so you subtracting is the same. I include aquí minus also. Bueno. This is trivial. Pero no, don't believe the matrix is tricky. And when you study multiplication, you see it's not the same. Okay, everyone follow me so far? Addition, subtraction, property. Now let's move into multiplication. Multiplication. But multiplication by scalar. So you have, for example, look at that. You have 2 matrices A and B. Okay. I need to multiply. Why need? Yeah. Multiplication 5A. Notice, when you multiply by 5, the matrix A, any entry, you multiply by 5. Now, 3 times 5, 15. Minus 7 times 5, minus 35. 0 times 5 is 0. And so, if you multiply 1 times 5, 5. So you multiply 2 times 5, 10. And you multiply 3 times 5, 15. It's super easy. But, important. 3 important. It's completely different to the determinant. Determinant, I suppose you remember, okay, for example, actually, determinant is only valid when it's a square. Suppose you have 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a matrix square, 3 by 3. We can associate very well one determinant. Look at the difference of notation. Matrix using a square bracket, determinant using the line similar to the absolute value, but actually it's totally different idea, no? But it's the notation. Some book or some article, something, is denote like a DET. DET is determinant of this matrix. This and this is equivalent. But the thing I try to explain is, now, if you multiply by 5, the determinant, we studied last time, we have the property that you multiply by 5, any row or any column. Suppose I am doing it in that way. 5, 20, 35. And the rest stays the same. This is a property in the determinant. You make a decision what row or what column you decide multiply by this scalar. And the matrix, no. In the matrix, when you multiply by a scalar, you multiply everything. Everything. Because it's totally different idea. It's totally different idea. Determinant look like a function, and the matrix, no. Matrix is the array of value. Of course, associated with the system, maybe, or another thing, but it's totally different idea. It's important to understand this idea. Okay, this the matrix is multiplied by scalar, super easy. Likewise, you have B and multiplied by 3, 3 times 5, 15, 3 times negative 2 is negative 6, and 3 times 8 is 24, and 3 times 3 is 9, and 3 times 2 is 6, and 3 times 1 is 3. This is 3B. Who is B? This is B. Okay, super easy. Now. Okay, more complicated. More complicated is matrix multiplication. This is more complicated. Not too much, but it's more complicated. Okay. In this case, you have two matrices, C and D. And the matrix C, row 3 column, 2 by 3. And the matrix D is 3 by 2, 3 row and 2 column. Okay. And if you pretend to multiply C times D, the most important thing you have to check in is the dimension. So you see, I try to explain here. Look, C dimension is 2 by 3, D is 3 by 2. If that number is perfect coincident with this number, so in other words, the amount of column, 3 column, que is the second number in the dimension, is equal to the number of row and the second matrix. Oh, perfect, matching, and we can perform the multiplication of the matrix. Otherwise, no. And the new matrix we obtain, I call E, capital E, is 2 by 2. How do you know that? Because this is 2 and this is 2. So this 2 is this, and this 2 is this. So when I perform the multiplication and the way I want to explain now, I don't explain it so far. I want to explain now. You obtain a new matrix 2 by 2. And basically 4 numbers. 1, 2, 3, and 4. Okay? Okay. Let me try. There are many ways to do this. I want to explain at least 3 different ways to multiply 2 matrices. And you select the way you prefer. And also we can do using the software also. Suppose again the same example, C and D. C and D I copy, but I copy in one corner here. Here I make a decision to start the multiplication C times D. I realize that the new matrix is 2 by 2. And you multiply, look, to find that value, E11. You multiply the row of the first times the column of the second. Like that, I try to illustrate a matrix 4 to understand much better, I suppose, no? So this matrix, this, que is the first row of C, obviously it's a partition, no, of C, it's not entirely C, it's one piece. Is 1 by 3 because we have 1 row and 3 columns. And taking the column of D, the first column, que this is 3 by 1. Okay, to say matching perfect the dimension because 3 and 3 matching perfect the dimension. However, the answer that we obtain actually it's no matrix because it's a, well, actually it's a matrix, but it's a matrix 1 by 1, and 1 by 1 is a scalar. It's just a number here. And how you obtain this? Doing like a dot product. Very, very similar we studied in trigonometric. You multiply 2 times -1, que es -2. You multiply the first component, the second component is -30, and the last component is 8. And together is 24. Okay, so this number is -24. Likewise, if you make a decision to find the element of the N3, that's the technical name, E12, so located in the first row, but the second column now. Well, so you multiply, you multiply again the first row of C, but now multiply by a second column of D. Okay, this. Similar, another dot product. You multiply 2 times -6 is -12, and -3 times 5 is -15, and 1 times -3 is negative. Everything is negative. Negative is -20. Let's say here is -20. And what about the rest? Well, the rest is similar. The rest is you want to obtain e to 1. You see in another slide, I need to multiply the second row, and not this anymore. Multiply the second row of C time the first column of D. This one. Okay. Let me see in the another slide. There you go. If my goal is determine E21 to 1, we see now the row 2 and the column 1. You perform the famous dot product in between two vectors. Yes, multiplication component by component and adding each other, well, adding or subtracting depending on the sign, algebraic. And finally, E to do is the multiplication, the row 2 in C and the column 2. So 2. Okay. You copy separately if you want. If you not necessarily copy separately, you mentally can do that. Multiplication -4 times -6, multiplication -4 times -6 is 24 positive, and 7 times 5, 35, and 0 times -2 is 0. And the answer is 59. Therefore, the fantastic conclusion is that the multiplication, this matrix, of course, in this example, no, is this answer. Look. Okay. So this matrix, remember, is 2 by 3. This matrix is 3 by 2. No, 2 by 3. All right. This is 2 by 3. And this is 3 by 2. Yeah, you're right. See this number matching perfectly. Okay. And we get 2 by 2. And the answer 2 by 2. Look, 2 by 2. And any component I compute separately is -24, -29, 74, and 59. I promise you see another more clear example, more elementary, to understand the multiplication of the matrix. And also, if you want the double checking, you can double checking because in the algebra we can do multiplication of things. Let me try to do one more example of the multiplication. No, a ver. Yeah. Okay, no, same example, but doing in different way. Look, it's the same example, but I want to decompose the problem because you can create partitions. Okay, look, this is interesting. If you take the matrix C totally, and multiply by one column, is possible or no? I don't know. This matrix dimension is 2 by 3. Look at that, 2 by 3. But you take one column of D, this new column is 3 by 1. So 3 row, 1, 2, 3, 1 column. This matching perfectly, and you obtain one new matrix case 2 by 1 case. And the multiplication is similar. You multiply 2 times -1, 3 times 10, 1 times 8, and you obtain that number. Likewise, you multiply is similar, but it's another organization. You organize like a row or column or no. You take the first entire matrix and multiply column by column of the set. It's one possibility. This is, we can do several partitions, always matching very well the dimension. You verify the dimension matching 2 by 3, 3 by 1. Suppose I copy again to find the second column of the matrix E. You take the matrix C again here. I just copy entire matrix and you now select the column 2. And multiplication. It's the same arithmetic, but it's another organization. Doesn't matter what way you select to do by hand. Another possibility, why not? Let me try to analyze another possibility. Is suppose another organization. Oh, no, I want to do differently. Look. Differently. Suppose now, can I take no column? I take rows. I take the row number 1 of C and you multiply it by the entire matrix. I think I try. So this is 1 by 3 because we have 1 row, 3 column, and this is 3 by 2. The matching perfect dimension, and the new matrix is 1 by 2, que es only 1 row, 2 column. And the multiplication is simple. You multiply this times this, this times this, this times this, and you obtain this number. And the same number multiplied by -6, +5, and -2, and you will take the same. Also, conclusion, guys, you can do different kind of partitions. You separate column and row, and your organization, and you obtain 1 by 1 entry. Or no, you select the entire first matrix and the different column of the second, or why not? The different row of the first and the entire multiplication by the entire second matrix, and you obtain the same result. Let's practice another example. Suppose this. Oh, this is easy because it's 2 by 2. So not necessarily the matrix you multiply must be square. No. Rectangular maybe. So imagine the dimension, but square is clear, can matching perfectly because this is 2. This is 2. And the new matrix you obtain after the multiplication is 2 by 2. But the thing I try to illustrate is that the multiplication of the matrix is not commutative. Unbelievable. Okay, suppose the matrix E is 3, 5, 1, 2. Time. The matrix F is 1, 2, 3, 4. So this is the matrix E, and this is the matrix F, and the operation that I want to do in between them is time. Okay, so now I expect another matrix 2 by 2. Let me call E11, E12, exactly the same, E21. Remember the double script indicate the first script indicate the number of the row que this element belong, and the second is the column, no? So this is row 1, therefore any element in this row start 1, 1, 1, 1 or 1, 2, and row 2, and column 1, and column 2. Okay, this is normal international notation that we use in this. Double script to indicate the position of the entry. Okay, so now let's do it. It's not important now. The important is that E11, you multiply this times this. Entonces es obvio que es 3 plus 15. 18. Wow, look at that. E12. Well. Yes, you multiply now. Again 1, pero multiplication by 2. Entonces es 3 times 2, 6. Plus 20, no? Because 5 times 4 is 20. 26. Boom, I get that. E1, no, I did 1. 2, 1. So I finish with the row 1. Entonces now I need to switch in to row 2 and column 1, ¿no? Entonces es 1, 1 es 1, 1 is 1, and 2 times 3 is 6, is 7. Okay, cool. And finally, e to 2 is the multiplication. Well, the second row and the first with the second column of the second. Entonces we have 1 times 2 is 2, plus 2 times 4 is 8, is 10. Okay, and you formate my matrix is E times F et al.
So I have a question. For E12, how did you get 20?
12. How you get what?
For an E12, how did you get 20?
Okay. E12 was the multiplication, mister. Look, the multiplication, the row 1 and the column 2. So when you multiply, let me use another column. 3 times 2 is 6. And when you multiply 5 times 4 is 20. It's 26. Got it?
Yes.
Okay. The rest is okay for you?
Yeah, I understand it now.
Okay, cool. You consider necessary doing the, okay, I consider it yes. So let's do it now, the multiplication. I change the order, look at that. I change the order. And now I want to multiply F times E. Who is F? F is 1, 2, 3, 4. That one. Multiplication, 3, 5, 1, 2. Normally, in the arithmetic you see before in my life, the order of the multiplication doesn't matter. You get the same answer. However, in the matrix, no. And the reason is clear, because the matrix is more than one number. It's multi-dimension, and the ordering is important. In the addition and subtraction, no, but the multiplication, yes. Okay, let me try. Let me try to find E11, E12, E21, and E22. These double secret indicate the order guide. To multiply now the row 1 and column 1. It's obvious que es 3 times 1 is 3 plus 2 is 5. Now I want to multiply 1, 2. So now I change now the column and the second by 2. So it is 1 times 5 is 5. And 2 times 2 is 4 and 9. Okay, now I finish with the row 1 out. And now I dedicate my time multiplication. This gets 2 row in the first one. And bueno, first of all, column 1, so es 3 times 3 is 9. And 4 times 1 is 4, 13. And 2 is multiplication now, row 2 and column 2 of the second, que es 15, 3 times 5, 15, plus 4 times 2 is 8, 23. Okay? The thing I try to illustrate is que the multiplication of the matrix in general is no commutative. So, in general, E times F no equal F times E. I promise that you see one particular example in which, yes, it's equal, but not always. I suppose that the majority of a scenario, the multiplication of the matrix is totally differently. Therefore, be careful when you are doing multiplication. Entonces now, to avoid any mistake, you need to specification. Si you pre-multiply pre-multiply or you post-multiply. What mean that? Suppose you have a matrix A and you pre-multiply by one matrix A, I call it E. Pre-multiply by E. Now, pre indicate before. This is pre-multiply. Suppose now this is a scenario, you have A and you post-multiply S after. This is E now. Post-multiply by E. E, you need to be aware that this answer and this answer is not the same. Okay? Okay? You understand very well? So let me summarize something. Let me summarize the most important property for the multiplication matrices here. Let me make a zoom this slider. Look. Okay, in general, the multiplication is not equal. It's not commutative property. So you define pre-multiply and post-multiply. This idea is clear. I use it in the future. And not in another lecture, in this lecture, we use pre-multiply, post-multiply. This is the important. So the first property is associative. Unbelievable. Associative is multiplication 3 matrix, ABC. ABC. You can multiply if the dimension matching. Entonces, it doesn't matter that you multiply this first, C matching, and the answer AB after you multiply by C. Or you ABC again, you make a decision, multiply B and C first and after A. Notice that you don't change the order. So you switch in the order, so we have a big trouble. It's not commutative because with the same order, the order of operation you can change. This is the typical associative property, but not commutative in general. The A and B and A multiplication is not the same. I use in general A and B, not E and F. Okay. And the famous distributive property that we use every day in algebra, if you multiply this and this, and this and this, we can use it also in matrix. Okay? Okay, distributive property, yes. Associative property, yes. Commutative property, no. In general, in particular example we want to study now, yes. Okay, let's move on. Maybe the question will fly in the professor. And what about division of the matrix? No, it's not defined division. It defines another similar thing, is inverse symmetry. What is inverse symmetry? Look, you have suppose the original matrix A. Wow. The original matrix A. And the inverse matrix, another matrix, can only exist on two conditions. Condition number one, the matrix must be square, no rectangle, square. 3 by 3, 2 by 2, 4 by 4, 5 by 5. And the matrix is non-singular. What means non-singular? So one matrix singular is the matrix that the determinant is 0. So this is a classical example. Suppose in Kramer rule, D is 0. When you compute x is equal to dx over d, you divide it by 0 undefined, to be undefined. This matrix has that property that the determinant is 0, is called singular. And to find the inverse matrix, no singular. Okay, so the determinant is, you know, one number, 5, negative 1, 20, negative 100, positive, negative, but no zero. And I take advantage of this important property, is when you multiply any matrix times its inverse, you can interchange. It doesn't matter if it's post or pre-multiply. It's unbelievable. I want to illustrate in one example now. And the answer, each other, when you multiply each other, give me identity matrix. I recall que identity matrix, suppose identity matrix is a matrix, suppose identity matrix dimension 2 is a matrix like that. 1, 0, 0, 1, 2 by 2. Identity matrix dimension 3 is 1, 1, 1, 0, 0, 0, 0, 0, 0, and so on. Identity matrix 4, we have 16 elements. The main diagonal is always positive, it's always 1, sorry, and the rest is just 0. This is called identity, and this identity matrix is nice because if you multiply any matrix time identity matrix, the answer is the same matrix. So this identity matrix work like a big multi-dimension 1. It's exactly the same when you are in arithmetic, you say 2 times 1, no, it's 2. But this 2 is a scalar because it's 1 by 1. But this 1, so the identity matrix 3 will behave like a one big 1 in 3 dimensions. Of course, this terminology is not used in the book. It's using this. Do you understand very well this? And we have different ways to compute the, okay, the question can fly in there. Bueno, professor, okay, I understand. I understand que es inverse. When you multiply by the original, give me identity. Nice. Okay, what is the application? How you find that? What is the formula? Well, there, I want to explain 2 different formulas. Yeah, I want to explain also, of course, in GeoGebra. So don't frustrate, que this is too long, pero no complicated. And the long with solving in the software. Right? Okay, let me try to explain the formula first. The formula to compute inversa is look, the inverse matrix is equal to the adjoint of the matrix original is given A. So this is given, no? Okay, I need to find this. This is my goal. The inverse. Divided by determinant of A. Es obvio que this determinant is non-zero because default, I suppose que the matrix is non-singular. So you discover que the determinant is 0, definitely you say, Professor, the inverse do not exist. Okay. What about adjoints? Adjoint is the matrix of the cofactor. Let me explain the matrix of cofactors. You have one given matrix. Okay, I want to explain the theoretical part, but I promise that I am doing a couple of the example in 2 dimensions and 3 dimensions. Suppose you have 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the matrix. Yeah, I need to find the adjoint of the matrix. Also, it's a matrix formed 3 by 3 also by cofactors. What is the cofactors? For example, cofactor 1, 1 is the cofactor that you form when you delete mentally this row and this. So it would be one new determinant. Let me copy a small. So C11 is another determinant, of course smaller, okay, formed by 5, 6, 8, and 9. Do you understand this or no? Wow. Entonces, of course, nobody write like that. It's a pedagogy idea. I write complicated. You copy separately, you compute it, you put just a number. Okay, by the way, it's 45 minus 48, que es negative 3. Okay, but now to understand what comes from this, we have different cofactors. Cofactor. Actually, we have 9 cofactors, no? Because it's 3 by 3, no? 9 cofactors. The cofactor, let me try now, the cofactor, erase this. The cofactor 1, 2, this was the cofactor 1, 1. This is the cofactor 1, 2. This is the cofactor 1, 3. Let me try at least to do at least one row, because the rest is obvious, it's the same intuitive idea. You eliminate, delete the row 1 and column 2. And the number that stay alive is 4, 6, 7, and 9. Okay, you compute this determinant, and this is the cofactor. Okay. Now, entonces now 1, 3. Bueno, 1, 3 is, you delete mentally in your mind 1 and 3. Ooh, so we have 4, 5, 7, 8, and so on. Do you understand this idea, right? Remember, again here I delete, it's a cofactor to 1. I delete row 2, column 1, cofactor to 3, to 2, sorry. To 2 is row 2, column 2, to 3. This is 3, 1. This is 3, 2. And this is 3, 3. I forgot something important, but I don't forget here. Transpose. What means transpose? So you determine the adjoint. Let me explain more clear. The adjoint is two things. Is the matrix of the cofactors. I compute that similar to this, but you transpose. What mean transpose? Transpose is S, not T. Transpose is easy. Transpose is suppose one matrix. Suppose one matrix. Suppose one matrix. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9. I want to transpose. The symbolic way to indicate transpose is 1 T. When you see one little T here, like it's pointing, the action is transpose. And the action for the transpose is change the row for the column. Okay? It's totally permutation. So you, for example, is equal, and you copy now, this is the row 1, no? You copy now like a column 1. And you transpose the row by column, or the column by row. This is 4, 5, 6. And this is 7, 8, 9. Okay. So it's complicated. It's very complicated because you need to find first the cofactor matrix to long process. After you transpose, okay, I get the matrix, and after you divide one by one by the determinant of the 8 matrix. Okay, actually, this is just a number. Suppose que es 20. You divide by 20 here, by 20, by 20, by 20, one by one, by 20, by 20, by 20, by 20, one by one. So the formula, let me repeat again. It's complicated, but no, don't worry too much for this. Is the inverse matrix is step number 1, compute the cofactor. After, when you finish the cofactor, gets too long, you spend 20 minutes doing that. Just 3 by 3. So you are doing 4 by 4, you spend 2 weeks. And now you transpose, and after you divide by determinant of the original matrix. This is the formula. But I simplify the thing in 2 by 2. Look at that. And 2 by 2 always easy. So my idea in this chapter is everything 2 by 2 we can do by hand. 2 by 2 by hand. Well, you can double check it if you want in the algebra, but not necessarily. It's possible to do it by hand. Suppose this example. Entonces now you see compute the inverse matrix. Let's do it. Let's do it. Okay, first of all, I propose this sequence of a step. You compute the determinant. So you temporarily, you forgot this square bracket, get the notation for the matrix. You put the bar, vertical bar, get the notation for the determinant. Inside you put the number, no, 3, 5, 1, 2, and you apply the thinking you know about the computation of the determinant. This is 6, this is 5, and 1. Cool. I create easy example. Okay, 1, just when you divide by 1, you are doing nothing. Let me try to find the cofactor matrix. Cofactor matrix, C. Let me call capital C cofactor. And cofactor is, look. What is the cofactor in this position? You delete this and this. Take 2, no? Do you see? Take 2. In this case, just a number, no determinant. Okay, you delete mentally the row 1 and column 1. And this is 2. And this 2 is positive or negative? It's positive. Remember the sign of the cofactor. The cofactor, remember, ese minus, okay, when you delete, but the cofactor have the corresponding sign. This is plus, this is minus, this is plus, this is minus. All right, this is minus, this is plus. Because look, it's 1, 1 is negative 1 raised to the second power. 1 plus 1 is 2. 1, 2 is negative 1 to the cubic power. 1 plus 2 is 3. That's the reason it's negative. 2, 1 is negative 1 again, raised to the cubic power, because 2 plus 1 is 3. This is the reason it's negative this. And the last one gets 2, 2, and negative 1, 2 plus 2 is 4. And when it's even, it's positive. Okay, so the sign of the cofactor, I try, you know, to summarize, to condense it in one extra matrix. Okay, just symbolic matrix to indicate the sign of this. So these two is possible. Why is positive? Because I know this idea. Okay. What about cofactor 1, 2? I did it mentally. 1, 2. It's 1, but actually it's negative 1 because this sign. What is the cofactor 2, 1? I delete 2, 1, 2, 1. F5. F5, but a negative 5. And finally, the cofactor 2, 2, you delete this and this is 3. Oh, it's 3. But it's positive 3 and negative. It's positive. So this is, capital C is the cofactor matrix. It's super easy. It's 2, 1, negative 1, negative 5, and 3. What should I do now? Cofactor transpose. Cofactor transpose, you change, for example, this row to column. 2, negative 1, and this negative 5, 3. Boom. And this is a cofactor transpose. Look at that. I did that. Cofactor transpose. In order to find the inverse matrix, you divide by determinant, but determinant. This example I create is 1, and when you divide by 1, it's the same. So this is when you divide by determinant is 1, divided by 1, divided by 1, divided by 1, divided by positive 1. The inverse matrix is the same. 2, negative 5, negative 1, and positive 3. Okay. But I need more clarification. Okay, this is the procedure, it's a formula. Well, it's no big deal. I try to memorize. However, what is the important property of this? Look at it. Suppose now, okay, to verify that we are doing well or no mistake, I try I try to multiplication, because you know very well how you multiplication. The matrix in this example time is inverse. So let's do in the multiplication. Look at that. Okay, this is the matrix A. Let's give it at the beginning. And this is the matrix A inverse. Okay, I try to find using the formula. And when you multiply A times A inverse, surprise. When you multiply this times this is 2 times 3 is 6. Let me try to do my best. 6. Where come from this 6? 3 times 2. And 5 times negative 1 is negative 4. The answer is 1. Oh, and that one I copy. Okay. Now. I multiply now. In order to find, for example, that number, okay, 0. I don't know if it's 0 or not. You multiply the first row and the second column. Bam! So we have 3 times negative 5 is negative 15. And 5 times 3 is positive 15. It's 0. Wow, cool. This 0 is this 0. Likewise, when you now switching to another row, this and this is 1 times 2 is 2, and 2 times negative 1 is negative 2 is 0, and this 0 is that 0. Okay, and the last is multiplication times this. So it is 1 times 5 negative 5, and 2 times 3 is positive 6, and the answer is 1. Wow! And this is this one. Conclusion. When you multiply any matrix times its inverse, it doesn't matter if it's pre-multiply or post-multiply. I prove here post-multiply. Interchange, and the answer is the same. Give me identity matrix. Oh yeah. Identity matrix of the same dimension. So suppose this is 2 by 2. 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 And give me identity matrix 2 by 2. Okay, you know, any identity matrix default you suppose is a square, and you indicate only one number get dimension. Just this. You follow me? So far, too much information, no? Okay. Let's relax a little bit. Let's move on to GeoGebra, and you see how we compute it in GeoGebra, the inverse matrix, and how you verify everything. Super nice. Okay, let me try. Okay, this is, we take the same example, 2 by 2, after I promised doing another more complicated 3 by 3, but this is easy. Okay, there you go. Okay, you let me know if you see my GeoGebra. Share screen, switching to GeoGebra. Do you see my GeoGebra?
Yes, we see.
Yes, okay, cool. Let me erase everything, because I never use it anymore. Determinant now. When you delete the matrix editor, automatically is delete everything. Okay. Suppose the matrix is given at the beginning. It is 3, 5. Let me use this 3, 5. Oh, what happened? 3. Hey, what's going on? Well, let me use my keyboard. 3, 5, 1, 2. 1 and 2. Okay, this is my matrix A. I create a matrix. The reason is because in the matrix editor, you have an array of numbers, but you don't know, so you want to categorize this like a matrix or just a table or just a list. But no, it's a matrix because I am working with the matrix. Yeah, I rename like A. Okay, cool. Now you go to the cast, que is the brain of this, and you type in inverse. Pero I don't know where invert. Okay, it's a invert. No inverse, invert. Don't ask me why because I don't know. Invert matrix. It's A. Presented, bang, and this is the inverse matrix. Let me try to compare 2, -5, -1, 3. Cool. Okay, now I want to take advantage, and why not multiplication in different order. Multiplication who? Multiplication A time. You press time is, a shift 8 after. Multiply by what? By what? By invert of A. Presented, bang, identity matrix. Okay, but I want to do in both ways. It doesn't matter. Okay, it's inverted now first. Okay, invert who? Invert the A. Multiplication. Time, A. That order. Again, it's identity. So I visualize, super clear. Super. Que in GeoGebra we can compute it perfectly. The inverse matrix do it. Not necessarily 2 by 2, 3 by 3, 4 by 4, 20 by 20, and you are doing 1 second. Okay, by hand is crazy. Okay, let me try now to come back to the whiteboard. I want to show you one interesting thing. Okay, let me try. Okay, switching to whiteboard. Okay, I suppose you see whiteboard now. Yes or no? Okay, Gustavo. Look at that. So now I am to find shortcut to make easy my life. I discovered that formula. Oh, that formula is the formula to compute the inverse matrix in 2 by 2. So this formula is not complicated, cofactor. No. Because the cofactor is just one number, no determinant. Entonces, my formula is relatively easy. Let me try one more time. Okay, suppose I need to find the inverse matrix of 3, 5, 1, 2. Suppose I have no computer. I try by hand, or the professor say it by hand. You compute that part first. And that part, hello, that part is determinant, A, B, C, D. So when you compute A times D plus minus B times C, is 1. By the way, I did before, this is 1. Let's do it again. This is 3, 5, 1, 2. This is 6. 3 times 2 is 6 plus. And 1 times 5 minus. Is 1. Now this is 1, this is 1 is invisible. 1 divided by 1 is 1, invisible. So the only thing I need to do, divided by 1, but si it's not 1, it's 2. You see in the review packet, I have several examples of this. Okay, maybe it's 5, entonces 1/5 is the fraction. Entonces now, your permutation, you see your permutation, D, so A is 3, B is 5, C is 1, and D is 2, no? So now, in the inverse, we have D here, que 2. And we have minus B, and B is 5. And C negative again, because it's, the sign of the cofactor in the corresponding position. Okay, it's positive, negative, positive, no? That is the reason that you have that negative, ¿no? Entonces es C, who is C, who is negative 1, negative 1, negative 1, and D is positive 3. In conclusion, it's super easy. You permutation this and this, swap 3 and 2. That is the reason that D swap. And B and C stay in the same place, but you change the sign. And divided by determinant, in this case was 1. Just say 1 is invisible. Nice. I love you. This is it. Okay? And that's it, no? I have another way. I have another way that I want to illustrate by hand and also in GeoGebra. Let me try. There you go. Look at this idea, it's very, very interesting. It's for the student that don't like the formulas. If you don't like the formulas, there are another possibility to compute the inverse. Let me show you how. Okay, make a zoom to understand this. What is the essential idea? The essential idea is, look, don't try to understand this. The idea is, you have a matrix. You need the inverse matrix. Therefore, you create one augmented matrix, big one, gets formed by the original matrix. In our example, we are doing S3, 5, 1, 2. This is matrix A, that one. And in the right hand side of the augmented matrix, you put the identity matrix. And doing row operation similar to the echelon, to the reduced row echelon, you try to convert several steps to manipulate, to change this in order to get in the left hand side the identity matrix now, and magically happen that in the right hand side you have the inverse matrix. It's a one possibility, no formula, just row operation. Let me try. Do you understand the key idea? Okay, let's do it. Suppose this example. I create the augmented matrix. Let's do it in GeoGebra also. I want to explain how. This is the original matrix it's given at the beginning. I put together with the identity matrix dimension 2, the same dimension. Okay, cool. So now I try to do my best in order to create identity matrix in the left part. Automatically in the right part you get the inverse. So I propose this for operation. You swap row 2 and row 1, swap, because I need the one here, que es the pivot, no? And the pivot is my friend, que help me to continue. So now I create this row operation, -3. Why -3? Because this is +3. You take the same number with the opposite sign, you multiply this factor, que es -3 now, time the element in the row 1, que es the row que contain the pivot, row 1, and plus row 2 and stores and the new row 2. And when you are doing this operation, it's obvious 0. Is -1. Let me try to understand why -1. Because it's -3 times +2 is -6, and -6 plus 5 is negative. Likewise, multiplication this and this is 0. 0 plus 1 is 1. And multiplication by this is -3 plus 0 is negative. Okay, because at least I have this one and this 0. I need this one and this 0 to finish. So now I propose you one elementary idea. You multiply the entire row 2 by -1, so you change the sign. Now it's 0, 0 times -1 is 0, -1 times -1 is +1, nice. This is the second pivot. And this is -1, and this is positive 3, because -3 times -1 is positive. Okay, so the last step is easy. Is I need to create this 0 here. Therefore, I multiply by -2, get the same number but opposite sign. Row 2 gets the row when you have a pivot. This is my second pivot plus row 2 equal row 1. So when you multiply by -2 times 0 is 0, plus 1 is 1. Cool, stay the same, no change. The part I did before. This is the beauty of that. Now you multiply -2 times 1 is -2 plus 2 is 0. I create that 0. I multiply -2 times 0 is 0 plus 1. Ahora -2 times -1 is 2, and 2 plus 0 is 2. And finally, -2 times 3 is -6, and -6 plus 1 is -5. And you see how magically it's science fiction. This is the identity matrix, dimension 2, and this is my inverse matrix of the original matrix. Okay, I give using the formula, but this is another procedure. This is another procedure. Let me try the rest of the time that we have to do in GeoGebra in this new way. And you, in the test, you are doing in the way you prefer. I don't care. The method, I care the final answer. Okay. Let me try. Okay. I'm always confusing. Switching to GeoGebra. Okay. Do you see my GeoGebra window?
Yes, we see it.
Okay, cool. Okay, because I want to erase everything. Well, I can use it, but no. Erase. Because this allows me erase everything. Because I never in this moment, actually, in the test, the reason I explain different way is because you feel comfortable to apply anything in it. So suppose que you copy the famous 3.5. But you now copy here the matrix in the same dimension. 1, 0, 0, 0, 1. Okay, now this is my original matrix. I just copy, paste in the place you want. Here I copy the identity matrix, and you put together augmented matrix. And this is my new matrix. Okay, by the way, this matrix is a matrix 2 by 4 because we have 2 rows and 4 columns. I create this matrix. Bang! I don't want to rename. M1 is okay for me. Now I go to the cast and you apply the famous reduce row echelon. Reduce row echelon. Exactly we are doing in the first topic of this chapter. And you put the matrix 1. Bam, bam. And you present it. Bam. And magically happen que in the left part, now we have the identity matrix. In the right part, we have the inverse matrix. Exactly the same we are doing in the another function that is invert. Do you remember invert? Let me create this matrix now. Wow, matrix 2, M2, and you put invert. In cast you go invert, invert of what? Of the matrix M1, 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 presented. N1, no, N2, sorry, N2. And you see that this matrix is exactly the same as this. Okay, at least the right part. The left part, of course, is like this. Okay? Okay. Now, the rest of the time we have, I try one more time to illustrate. Okay, let me try to come back to the whiteboard. Whiteboard now. Okay, whiteboard. I try to illustrate the formula, no, of the inverse matrix. Look, let me try this slider and this slider. This no. Okay. Look. Suppose que I have more complicated problem. Okay, no problem. More complicated, in which you have the matrix M. Let me copy my piece of paper, the matrix M, and the matrix M is 1, 2, 3, 0, 1, 4, 5, 6, 0. But my goal is compute the matrix inverse. Okay, so I can do in different way. You can do using the formula, or we can do using the augmented matrix and apply the famous reducer row echelon. Let's do it here by the formula. The formula is, okay, step 1, my opinion, is compute the determinant. Okay, so now I immediately, in my mind, you put EET, or you put like that, it's equivalent 1, 2, 3, 0, 1, 4, and 5, 6, 0. See, there are no problem, no restriction, no limitation. I prefer doing always using the first row. I don't know. So is 1 is the first entry, multiplication by the minor, okay, minor is 1, 4, 6, 0. Well, we continue now walking for the first row. The second guy is 2. A 2, but actually minus 2 according to the position of the cofactor. Remember the sign of the cofactor is plus, minus, plus. So says the minor is, let me see. You delete now row 1, column 2. So says 0, 0, 4, 5, 0. Okay, plus 3. And the last determinant is, let me try, is delete 1, 3. 1, 3. Stay alive, 0, 1, 5, 6. Okay. Now 1 is nothing. Multiplication is 0 is 24, but minus 24. Minus 24. Remember, this multiplication is positive, or not exactly positive. You know, you don't change the sign, and here you introduce artificially negative 1. Minus 2 times, and this is 0, and this is minus 20. Actually, it's positive 40, no? Together, plus 3, plus 3, plus 3, plus 3 times. This is 0, and this is 5, but negative, that's 15. 15, no 5, 15. No, 5, sorry. 5. So 5 times 1 is 5. pero es negative, ¿no? Because you go over, es negative 5. Entonces we have minus 24 plus 40, minus 15, ¿no? 24 y 15 together is 9, 39, pero negative. And 40 minus 39 and 1. Okay, that is the reason that the determinant is 1. After I promise I want to verify in the algebra, if we have time or not, okay, the determinant of M is 1. Okay, now according to the formula, I know I need to compute the cofactor transpose. Okay, entonces now one possibility is, doesn't matter if you compute the cofactor and transpose, but the order is not important. Or you transpose and you find the cofactor of the new after the transpose. So now the original is in this order: 1, 2, 3, 0, 1, 4, 5, 0, 6. The transpose is the capital T, like exponent. You change the row by column. You have the row red color, I put like a column red. Blue row, column blue. And row green, column. And you apply, this is the most complicated, no, long part. In this super long part, you determine the cofactor one by one, or actually not exactly cofactor, minors. So you delete, for example, let's do it at least one. You delete, this is the cofactor 1, 1, and the cofactor 1, 1, you delete this and this. It's 1640, look, it's minus 24. And so on. It's 9 cofactor. We need C11, C12, C13. I know it's long, sorry. And you write the new cofactor matrix actually transpose, because we did before the transpose idea here. And I consider only the minor, but not the sign. The sign, I included this. Okay, this is a negative 24, actually it's negative because negative times positive is negative. And negative times negative positive, I adjust the sign. And this is the adjoints. And finally, in order to find the inversion matrix, you divide the adjoint matrix. Look at that. In order to find, this is the formula. This is the most important formula. You divide the adjoint matrix divided by determinant, but in this case the determinant is 1, so it stays. Beautiful. Do you follow me, guy, or no? Are you sleeping?
Yes.
Yes, what? Sleeping or clear?
Follow.
Follow me. Okay, cool. Okay, so let me try in the 5 minutes that we have, take advantage and doing this job little by little. No by hands, using algebra. Okay? Okay, let me try. Switching algebra. Okay. Do you see algebra or no? Do you see or no? Let me know.
Yes, we see it.
Okay, cool. I don't know why I stay here, but I delete this one. Okay, I copied my original. My original was 1, 2, 3. 0, 1, 4. Uh, 5, 6, 0. Okay. Wow, what the hell? I try to delete this one. Okay. Now I select, I determine, I create the matrix associated with these numbers, and compute the determinant. Determinant of M1, is the name default, I suppose. Gemini 1, exactly the same. Cool. Now let me try to find the inverse. Of course, you cannot see. Well, you can see you separate in different pieces. You separate in the 9 minors, and you compare one by one. But no, hello. I go directly to the point. It's inverse symmetric. It's invert. I know what the language of the GeoGebra is invert, no inverse. Okay, but I adaptate to the software. The software is amazing, so I take advantage of the M1. Pero wait, no capital. Es lowercase M1 because I suppose que it's not the same. Press enter. The answer is negative 24, 18, 5, 20, negative 15, negative 4, negative 5, 4 and 1. I copied in my piece of paper. This is the inverse symmetry. To verify that everything is okay, well, I do the multiplication of the N1 times the invert of N1. If I'm doing well, the answer would be the identity matrix dimension 3, que is 9 elements, but the main diagonal is 3, 1, and the rest is 0. Bang! I have the answer. Cool. Okay. I stop for a moment because the most important part is next part is the application of this. You see how, but we have no time. It's not too long, but we dedicate the, I suppose, the next lecture. I finish this part, it's short, not too much, and after we start review for the test. Okay, cool.
Yeah, thank you, Professor.
Pleasure, anytime. In a few minutes, I will send when I create the video. Okay, guys. Have a nice day.